practice set 5. So today it's going to be all about induction. While I'm solving this, while I'm going through it, if you have any question that has to do with induction, stop me, ask. Otherwise, if you have questions that have to do with tomorrow's exam in general, let's save them till the end, till we finish these exercises. And starting with exercise 1, mathematical induction on the following. So, first one, 4 divides n power 4 minus n squared. Base case, should be familiar with this. So the 3 steps are: step 1, the base case. So choose usually the lowest n that they told you. Here there's no n, but obviously it has to be greater than or equal to 0. Okay, now assume in the inductive hypothesis that up to n it's true. So n power 4 minus n squared, you have this now as given that it is divisible by 4. You want to now do it for the next step, for n plus 1. Well, there's a subtraction, so you just expand each formulae and then you subtract them. You're gonna get this thing. The reason you get this is because n power 4 minus n squared, you have this as an assumption that it is divisible by 4. Obviously, 4 times something is divisible by 4. You're left with this. Now, you can do 2 things. You can either assume that 6n squared plus 2n, you can assume it's like a whole new problem, and you have to now prove that this is divisible by 4 using induction. And if that leads you somewhere, great. Or go with the cases. We're trying to prove that this is divisible by 4. So n has 3 formats. Either it is divisible by 4, remainder 1, remainder 2, 3. Expand all of them, you'd reach it is divisible by 4 in each one. Second part, 4 power n at power 2n minus 1. Now, they did it in a way, you can check that solution, see what's up with that. Or you can do it like how we did a similar problem in the recitation, where we proved, I think, 4 power 5 or 4 power n minus something that was divisible by 3 or 4. So how do we do that? Base case, again, is easy enough. N is 0, 1 minus 1, you get 0, that's divisible by 4. Assume that for n, it is divisible by 5. So this is now given, modulo 5, it's going to equal 0. So it is divisible by 5. For the next step, step 1, 2, 3. For the last step, proving it for the next one. So for 2 into n plus 1 minus 1. This is just 4 2n plus 2 minus 1. It's as if it's 4 squared times 4 power 2n minus 1. So what's 4 squared? It's just 16. So it's like saying you have 16 of these 4 power 2n minus 1. And we'd like to see this. We'd like to see this given 4 power 2n minus 1. Just take one of these. So it's like 15 times 4 power 2n plus 4 power 2n minus 1. This is your given. You know that it is divisible by 5. And you have 15 times something, or 5 times 3 times something. It is divisible by 5. I found this way is more neat than what they're trying to do. Whatever works for you. Last part. Summation of this. Base case, it works. All you really have to do here is when you want to prove it for the next step. So in your assumption, you have from I is 1 till n. In the next step, it's from 1 to n plus 1. So just break it down. sum it from 1 to n, and then from n plus 1 to n plus 1, which just gives you this. This is your assumption, so you can write it. Now you just have to find the common denominator, find some format, and you're done. So this is just like algebra, just math. There's no proofs here. Was that exercise 1? Yes. So if you had any problem with exercise 1, if something wasn't clear, let me know. Just simple induction, base case, hypotheses, and then the induction step. And in all of them, we were trying to find the inductive hypotheses in our inductive step. So when I assumed that this is divisible by 4, I was trying to find it. When I assumed that this was divisible by 5, I was trying to find it, and so on. Use induction to prove the following property about sets. Okay. So A1 union A2 union, all in brackets, intersecting with B. Can you like just distribute it on each of these sets? Well, step 1 base case is for n is 2. Like you have to have at least 2 sets, right? So A1 union A2 intersected with B. You can distribute this by distribution laws. Union A2 intersection with B. Okay, now in the second case, you assume that all of this is true. So that yes, if you have up to n sets that are unioned and you want to intersect them with a new set, you can do this. Now what you should do for the next step. So let's find it. Yeah, so base case, our hypotheses. Now here. So now you just add a new set, an plus 1. All of the ones before, you can just assume that they're one big set. Like what's the union of 2 sets? It's just a set. What's the union of n sets? It's just another set, like this. So now it's just like one set union another set. Just like the base case, you can distribute it. But what is this? This is your given. So we're 5 minutes in and I've already said this 100 times. Every time you just want to find what you're assuming in your set, in your inductive step. So it's this thing, just expand. Therefore, yes, what you're trying to prove is true. 3. Define the following. Show that Sn is less than 12 for all n greater than or equal to 1. Well, the base case is just given, right? If I is 1, so S1, it's 12, already given. So easiest base case ever. Now you wanna assume that yes, Sn is less than or equal to 12. Wanna prove it for the next one. So an interesting idea is what they did. Start from Sn. So this is your assumption. You're gonna use it right away. You're gonna say, hey, Sn is less than 12. And now you wanna try to build Sn plus 1, which is just this thing. So any element is gonna equal this formula in relation to the previous element. So if this is n plus 1, you stick here as n. So now let's just build it. Start from Sn, 5 plus 100, logarithmic on both sides, times 4, blah, 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 blah. You reach this, which is less than 12. You're done. Could you have started from this way up? Guess, maybe. But it's much nicer to start from your given and reach what you're trying to prove. So there's exercise 1, 2, 3 already done. Exercise 5 is a classic and it's very nice. Fibonacci. So I'm not sure if they mention it, but this should be, or actually you might not need strong induction here. You might not need it. But anywho, Just like before, this time our element is related to two previous elements instead of just one. What's Fibonacci sequence? At any moment, the element you're currently looking at, it's going to equal the summation of the two previous. So the third element here is going to be 2. The fourth is going to be 3. 5, 8. So 5 plus 3 is 8. 5 and 8 is 13, and so on. What they're saying is, show that the sequence is going to be odd, odd, even, and it repeats. So here, 1 is odd, odd, even. Then we have odd, odd, even, so on. Base case. So for F1, it's going to be true, right? Like if you're working with, or actually it should be at least, for this thing. Sorry, my bad. For these, we want to prove it. So yeah, if K is 1, you're going to get F3 equals 3 minus 2. It's 3 minus 1. So just 1 and 2. What's F3? It's 2. It's even, and we're given that these two are odd. So for the base case, it's over. It's done. How they say it? For K is 1, F1 is odd, F2 is odd. Their sum is F3, which is even. Done. Inductive hypotheses assume it's true for some K. You have some K such that, yes, these are even. It's a K right here. Now you want to show it for K plus 1. So what's K plus 1? These guys. So what's the next step gonna be? Well, F3K, we just showed that it's even. Like we're just gonna be continuing. Like here, if you stopped before at here, now you just want to prove that the next thing is gonna be odd. So F3K is even. F3K minus 1 is odd. And therefore their sum is odd for this thing. In a similar way, you can show the next and the next, so that the pattern repeats. Any problem with this thing? Take a moment to look at it. Okay, so it was just breaking down each one of these. For the K plus 1, you stick it here. You try to, you got that it was, where are you? That it was odd. Then you stick this one. It was also odd. The last one was even. So the repetition, the pattern odd, odd, even, it got repeated for K plus 1. Exercise 5. Yes, Judd, do you have a question?
Yeah, for exercise number 4.
Yeah, what is it?
In this one specifically, I split it into 2 cases. I split it into case 1 where F3K is even, and then I proved that. And then for the other case, when F3K minus 1, F3K minus 2 are odd, I used F3K being even to prove that when you add an odd number, you get an odd number. And then through that way, I proved each one. Is that still okay?
Can you repeat? What were you, is the assumption, did you say this assumption, first of all, in your inductive hypotheses?
I
Like,
did, but I split the question into 2 different parts.
which are,
I
you want to
first of
prove
all,
that these are odd
yeah,
and this is even?
exactly. I proved that F3K is even first, and then I used that to prove that F3K minus 1 and F3K minus 2 are odd.
Okay, and then for K plus 1, you did the same?
Yeah, exactly. But it just took me way longer to do. That's the whole thing. Yeah,
Okay.
and this took like like 7 lines. It took me like 2.5 pages.
Yeah, I can hear the papers being flipped. Um,
Yeah.
okay, the only thing that bothers me with what you said is why did you have to prove that F3K is even and the ones before it are odd? Like this is your assumption. You assume that this is true and then you want to prove it for K plus 1. It feels like you assumed it for, like you proved it for K and then you proved it for K plus 1. That's the part I didn't really
No, I
understand.
assumed it. Sorry. I
Okay.
assumed it. Okay, I split it. I split it into two cases. The first one where they're odd, and the second one where they're even. And then I assumed for the even part that F3K is even, and then I
Mm.
solved for K plus 1, pretty much. And I did the same for the one before it. For the one after it. Sorry, the odds.
Mm. Okay.
It just
Okay.
took way longer.
I'll check it in detail in your solution. Okay, so congratulations. I'm gonna correct your assignment 5 definitely. Okay.
Okay.
But is it okay now? Do you get exercise 4?
Yeah.
Is it fine? Okay, good. Thank-
Thank you.
Welcome. Moving on. Exercise 5. N factorial greater than 2 power n greater than n cubed. We did something like this in the recitation as well, but I think it may have been n factorial and either one of these or something similar, maybe n power n. So it's all about finding the formula here. So find an integer n that makes the following true. So you just have to try a bunch of n's until you find that yes, n factorial is greater than this, is greater than this. So it's kind of like they're telling you, you yourself should find the base case of where this becomes true. And it's gonna be Sorry about that. Seems like every week, exactly between 5:20 and 5:30 p.m., my internet cuts off. You heard me say?
No,
Okay,
we can't hear you. No, we can't see the screen.
can you see the screen or not? Because I have it shared.
Now clear, we can hear you.
Okay, good. Okay, good. So I don't know what I'm gonna assume that everything before this you were able to not let me know. So the second case is for n factorial is greater than 2 power n. This is more intuitive because all you have to do is step 1, n plus 1 factorial, just obviously split it into n plus 1 into n factorial. So we can see our given, substitute it. I just want now to see that it's greater than or equal to 2 power n plus 1. I have 2 power n, I have n plus 1, and we're working where n is greater than 9. So n plus 1 is obviously greater than 2. Just put 2 and we're done. Let me know if there was a problem with x5 due to that. Anyway, exercise 6. Assume you can only use determine for which amount of postage can be formed from the blah, blah, blah. So find the base case where you can now start splitting integers into 3a plus 5b. We did something similar in the recitation. It may have been 3a and 4b. And we were talking about wires, but same thing, same concept. So I think it's gonna be, yeah, 8. So after 8, it starts to work. You can split all the into 3a plus 5b. Using mathematical induction, and then prove using strong induction. You can also do it in the normal, simple. Do that first. Previous. So all we know is that just an adding a 1. We want to find a prime b prime such that this, well, is, so you have a bunch of 3s and you have a bunch of 5s. That's the whole thing, right? You can so your current literally, so how do I do that? Well, if I remove 2 3s, sorry, 3 3s, that's like -9. Then I add 2 5s, that's +10. So the overall difference is going to be 1. So what I'm trying to say is, you have n split into a bunch of 3s and a bunch of 5s. If you have enough 3s, remove 3s, remove 3 of them. So a minus 3. You remove 3 of them, and you add 2 5s. If you do that, the whole difference is just going to be 1, which is what you want. You went from n to n plus 1 while still maintaining that you can split them into a bunch of threes. So this is what they're saying here. If you have enough threes, just remove 3 of them and add 2 twos. And you just, hey, let 3 and b plus 2. Plug in the equation to find out how many b's you have. It'll turn out that you have at least one b. It makes sense, right? We're working with integers that are greater than or equal to 3. So if you have less than 3 threes, that means you have at most 6, which is split into 2 threes. So you're gonna need at least one more 5 to make it all work. So you have at least one 5. So what can you do in this scenario? Well, remove a 5 and add 2 threes. When you do threes, that's going to be a plus 6. A 5, that's going to be 5. Overall, you added a 1. The difference is going to be 1. That's the gist of it, but they break it down into a lot of details. Time, and let me know if you have any problems with it.
Sir,
Yeah.
I'm facing a problem with strong induction.
We haven't reached strong induction yet. It's going to be the next part, but what's your problem?
The mathematical induction is easy, but strong need more steps, and these steps I cannot. I'm unable to understand.
But listen, let's solve the next part, which is about strong induction. So it's going to be the same problem, but now using strong induction, and let's see if we can try to understand that. Okay?
Okay.
That prove that the next thing, p of n plus 1, is true. So this is your hypothesis. This is what you want to base up to, and you want. So let's say it's k. You're going to assume it's true. So you have p of 8, p of 9, p of 10, and so on. You have a bunch of given let's do that k plus 1 is also true. So it's not that you have more steps, it's just that you have more premises. Okay? How will that help? Well,
So the only difference. So
I didn't hear you. What?
the only difference between strong induction and the weak induction is more steps or what, or the premises. What's the main?
It's just that you have more premises. It's a different sort of problem. Definitely, it's going to be slightly different, but it boils down to that you have more given, or you need more given in some scenarios. Here, it's not that you need more given, because obviously we just solved it using simple induction. It's just a different way of looking at it. Okay.
We need more steps in the base and inductive hypothesis, or only in the inductive hypothesis.
Can you repeat?
We need more steps in the base or the inductive stuff.
No, base case, it's the same. Inductive step, it's almost the same. So in the normal induction, what do we say? You do it for the base case first. So n is 0, for example. You prove that whatever you're trying to prove is true for this. Then you say assume true for n. Like for example, here n power 4 minus n squared. You proved that for n is 0, it is true. Then you assume that n power 4 minus n squared, it is divisible by 4. I'm throwing back to the first problem.
Yeah.
Then in the last step, you just have to prove for n plus 1. So just say, hey, n in n plus 1 power 4 minus this. Just prove that this is divisible by 4 and done. But all you have as given is this. You can't use more information than this. If we now want to say strong induction, step 1, just prove it for some base case, n is 0. Step 3 is going to be the same as well. You just have to prove for n plus 1. The only difference is in step 3, which is just words. You assume true up to n. Like everything up to n is true.
What do you mean?
Like p of n is true. So n power 4 minus n squared is divisible by 4. P of n minus 1 is also true. So n minus 1 power minus this thing by 4. And p of n minus 2, and so on. Everything underneath n is going to be true. You just want to prove it for n plus 1. Does the basis make sense? This is just how it is. You assume everything up to n is true. Okay?
We we always do minus n minus 1 and minus 2. Is there an and or a limit for that?
Obviously, until you reach the base case. Like, for example, until n is greater than or equal to 0. This thing. Like, if there's no limit on n, but let's say it's a million. This is wrong to say, but let's say it's a million, then a million, 900,000, all the way to reach 0. They're all true. You just want to prove it for 1,000,001.
One more question. Can you solve a proof by mathematical induction instead of strong induction?
It depends on the question. Like, for example, the one that we were just, or you can induction. If you can do some, definitely can do strong induction, because we see here, it's everything n and below. So obviously, if you can prove it using strong induction, you can do it using simple induction. But the other way might not be true. If you do it for simple, if you do it for strong induction, you might not be able to do it for.
Oh,
Well, I don't think what I said just made sense, but that's the whole problem. Where are we? I'm not sure what I said before, but if you have simple, you can definitely use strong. Because here you have given p of n, here you have given p of n minus 1, p of n minus 2, and so on. So obviously, if this is enough to prove it, then this is going to be more than enough. Like you have just more given. But the other way around, if you need these to make it true, the other way around might not work. Like maybe p of n alone is not enough. You also need n minus 1, n minus 2, and so on.
Okay, clear.
Okay.
Thanks.
Let's see now what they're saying. Remember, this is all about trying to break down n into 3a plus 5b. Do n plus 1. But we're not going to do it right away. P of n minus Let's try. What do we know about P of n minus 3? Well, we know that it's just n minus 3. You can write it as a multiples of 3 and multiples of 5. If you take 3 to the other side, 3 prime plus 5b prime plus 3. Okay, I can take 3 in common. But this doesn't do my proof because this is n. I want to try to do it for n plus 1. Let's see P of n minus 4. This is what we mean by strong induction. Like, this is true. You can break it down. And this is also true. You can break it down. What does this say? N minus 4. You can write it in the form 3a plus 5b. Same thing, only take 3 to the other side. You get n minus 1. So that also might not work. What should I use? If you get what I'm trying to reach. I think P of 2 is gonna be enough. So now if we try to say P of, n minus 2. This says that n minus 2 can be written as 3a plus 5b. Now add 3 on each side. I get n plus 1 equals 3a plus 5b plus 3. And you can take 3 in common. A plus 1 plus 5b. And you're done. You have this as given, n minus 2. So you can write n minus 2 as a multiple of 3 plus a multiple of 5. Add 3 on each side. You get n plus 1. And the right hand side is still a multiple of 3 and a multiple of 5. So n plus 1 is 3a prime plus 5b prime, such that a prime is a plus 1 and b prime is b. Does that ring a bell? Somebody's asking, strong means we substitute more values. It means you have more value, more given, more values to use. So yeah, you could have the option to substitute more. One, and you could have done the right-hand side of multiples of 5. So common, you could have taken 5 in common, but which given? You can work like you have n plus 1, 5b plus 5. You could have just subtracted 5 on each side, and you're gonna get all. I used 4 here. This is like reverse engineering. Okay. So any problem with this part? Like, are you starting to get what strong induction is about?
Yeah, almost.
Okay, let's just do more. Let's just do more strong induction. A different taste will be another idea. This time, exercise. Use strong induction to show that every positive integer n can be written as the sum of distinct powers of 2. So you power 0, 2 power 1, 2 squared to build some natural number. We have hints that we're gonna be using. Just assume that k is odd or even separately. Let's just go through the cases. So Base case, if k is 1, and we're going to be using strong induction here. Value that's less than k, you have that this value is true. Here they're using different variables, but it means the same thing. So you have p of 1, p of 2, and so on, all the way up to p of k. All of these are given. Like any natural number that's less than or equal to k, you can write it as a summation of 2 power something. Now you want to give you plus 1. Let's see. Two things. If k is even, that means k plus 1 is odd. What does it? What do we know about p of k? P of k is asking, can k be written as a 2 power something plus 2 power something? Yes, it is true due to our hypotheses. So it's written right here. 2 power m1, 2 power m. These are just variables. But we know that 2 power 0 is not here because it's even. If you add 1 at the end, these are all a bunch of evens. If you add a 1 at the end, it's going to be odd. But what about k plus 1? And plus 1 is just 2 power 0. So that's for the even scenario. We haven't used technically strong induction as of yet. So far, this is just simple induction. In order to prove k plus 1, in case k plus 1 was odd, we only needed k where k is even. What about the others? If k is odd, k plus 1 is even. So this idea no longer works, the trick that we just did. Well, k plus 1 is even though. K plus 1 divided by 2, remember this is a hint date, is going to be a integer. Like you can divide it by 2. This isn't really a fraction, it's just a natural number. This is the inductive step, the strong inductive step. We know it's strictly less than k plus 1. So it's in this range. K plus 1 over 2 is true. So you can do this. You can write k plus 1 over 2 as a summation of 2 power something plus 2 power something, and so on. Now what do you just crisscross? Multiply 2 on each side. So it's 2 times this, times this, times this. Expand. You're done. 2 power m plus 1, 2 power m2 plus 1, and so on. You were able to write k plus 1 as a summation of 2 power something. That makes sense. Here we did need strong induction, because when k was odd, we didn't just look behind us, or sorry, for pk plus 1. When p of k was just odd, this wasn't enough to go just right behind me. I had to go all the way, it's like halfway back for p of k plus 1 over 2. I needed the whole thing to be true in order to be satisfied. One more. You are building a pyramid with a square base using identical. So we're just building a pyramid using squares. What are the steps? First, build a square. Okay. So n by n. Center above it, another one, like on top of it as a 3D. -1, then n minus 2, n minus 2, till you reach the very top of the pyramid, and so on. If we want to build height 3, they give a specific example of how many you need. Write a summation formula to count the total number of racks needed to build this pyramid. Well, first of all, I needed n times n for the base. Then on the one right on top of it, and so on till I reach the first. So this is summing from 1 till n, I squared. Then you want to find a closed equation for this. This is a known geometric series, so find and prove using induction. This is our summation, and this is the closed. So now it's just another induction problem, similar to something we solved above. You want to summation from 1 to n. Case, then you assume, then you do the step. 1 to n plus 1. You just break it down as summation from 1 to n plus summation from n to plus 1, which is like plugging it in for just one value, which is n plus 1. So that's it for reduction, strong reduction simple, or function set, whatever you have for the exam. If you, I think Hassan, you get strong induction. I don't know. Let me know. We'll try to figure something out. Okay, so let me know now. You want me to pass over uncountable and countably, or do you have a specific problem you'd like me to solve? Okay, I'll go through the definitions in a second. Okay, let me just bring up the recitation 5. Or, yeah, it was 5. Okay, so okay, so first of all, you already know what normally what's finite is just you have a bijection from a set to another set, but n is something finite. Like, hey, you say let n be 100, then you can find a bijection from 0, 1, 2 till 99 to the set that you're working on. This is just what finite means. Like your set has a finite number of elements. And remember, a bijection is sort of like you're counting. If you have a bijection from set 1 to set 2, it means they have the same number of elements. So when you're saying I have a bijection from a set that has the elements 0 to 99 to this other set, it's like you're saying you have 100 elements. So that's for finite. What you want is ability, which is here. So it depends on the definition. Usually, if you tell me something is countable, I'll understand that it's either finite or it's countably infinite. So it depends really on your instructor, how he's doing it. So if Professor Bilal was saying countable means both finite and countably infinite, great. If he only said it was this thing, then you go with that. But let's see the definition. What does countably infinite or infinite mean? You have a bijection from the set n to the set that you're trying to prove. So they are both the same? No. Finite is different from countably finite. They're definitely different. But some people, for me, they're both under the category of countable. Like they're both countable, but they're different things. Okay, just like n and z, they're just different things. So this is a bad example of saying they're different, especially in a cardinality session. And so you have this bijection from the set n. So like 0, 1, 2, it never really ends. You keep going, and you have a bijection to the set that you're trying to prove is countably infinite. Uncountable mean it's not countable. So if you have a set that's infinite, and you can't find a bijection, like you can't find this thing, then it's uncountable. Now, let's do some example. Let's do an example of each. So the set z of integers, it is countably infinite. All you have to do is you have to list them in a way that works. So let's say 0, then 1, then minus 1, 2, minus 2, 3, minus 3. If I keep going like this, I'm gonna be listing all the elements in Z. Now I just have to relate them. So if this is my Z, I have to relate them to my set n. So 0 will go to 0. 1 will go to 1. 2 goes here. 3 goes here. And so on. As an explanation, this would be enough. But if you wanted to actually find the function that makes it work, it's going to be split. If you notice, if n is, if it's, let's say, even, what are we working with when n is even? So 0, because remember, the function takes you from n to z. So you take n from here, it takes you here to f of n. So when n is even, that means when I'm working here, so this is even, even, even. It's sort of like I'm going to the negatives, right? So 4 takes me here, 5 takes me to -3. It's like I'm going to the negatives divided by 2. Sorry, this is 5 and this is 6. So if I say n over 2 minus, is this enough? Let's see. When n is 0, f of 0, just 0 divided by 2, I get this. When n is 2, minus 2 over 2, I get -1. When n is 4, minus 4 over 2, I get -2. So yeah, it seems like the even works. What about the odd? It's just n over 2. Or is it just, let's see. So 1 gives me 1. 3, I want it to give me 2. Yeah, but it has to be the ceiling of it. Let's see if it works. 1 divided by 2, then let me here. So of half is 1, that's done. 3 divided by 5, the ceiling of that is 3. So this is what countably infinite means. You were able to find the bijection set n to the set that you're working with. So countably infinite, that just means that like the set you're working with, the size of it has the same size as n. Okay? So since they have the same size, the definition isn't just bound set n. Now that we know that the set of integers z is countably infinite, instead, like, I don't know, assuming the professor doesn't mind, like if he told you, yeah, you could use it, you could now say, hey, z, if I can find a bijection to some set S1, then it's over, and so on. So that's countably infinite. Another examples you can try on your own time, maybe the even integers, the negatives, like just the negative natural numbers, and so on. There's lots of countably infinite. There's Q. I'm not gonna go through this a lot. You've learned it in class. Like it's you write them, then you do this format. This thing is uncountable. Okay, so uncountable, you won't be able to find a bijection. So if you usually there's two ways to do it. There's two ways the problem could come. Usually, either you have to prove that something is countable. You have to do this. You have to find the bijection. If you want to prove that something is uncountable, you have to work with contradiction. You have to assume it is countable. So you're assuming that you do have a bijection function from n to the set you're working with. Then you reach a contradiction. In this scenario, if you want to go through the whole proof, what happens is not all the integers or all the numbers here are covered. So when you go 0 goes to the first element and goes to the second element. You're assuming that all the elements have been covered, but you can figure out a clever way where no, they don't know. they don't all get covered. It has to do with the decimal parts. And here you can use this link. It has a lot of interesting multiple choice questions. Did I answer you somehow? Do you have now some idea of what countable and uncountable is? Okay, good. Does anybody have a question? If you have something on uncountable, if you have a specific example you'd like me to solve. So, does it have anything else? By the way, Hassan, this is a nice question that shows you why you do need, like, what's the point of strong induction? It's when you need everything before the condition. I'll just go over this question as induction. Hopefully it'll clear some things out. Okay. So very quickly, I assume you sort of remember this. The idea here, if you have a pile of rocks that's between 1 and K is the number of rocks in pile 1. Yes, I just wrote pile here. Pile 1. And you have another pile 2 that has the same number of rocks. Okay, so K in both. Now, the question is saying, use strong induction to prove something. What's that something? Just take it as, so the game is you have 2 players, player 1, player 2. The game is saying, the problem is saying, player 2, as he's the second person to start, they can always win. They can always find a strategy that makes them win. I'm gonna tell you what the strategy is. If player 1 takes 5 rocks from one of the piles, like pile 1 or pile 2, let's say pile 1 without loss of generality, then what does player 2 do? He also takes I rocks from pile 2. So they'll do from the opposite pile. So player 1 takes I rocks from pile 1. Player 2 takes also I rocks from pile 2. How can we automatically know if the question is induction or strong induction, or is it not that simple? I think most likely it's going to be specified if a question is simple or strong. If it's not specified, like I said, start off with the mentality that you're going to be using simple induction. And if at any point you feel You'll just scratch the part where you say assume for n and say up to n. Okay, back to this problem. Okay, so let's see the base case. What's the base case? You have just one rock in each pile. So if player 1 takes the first rock, player 2 takes the second rock, and player 2 wins. Because the game says the winner is the last person to take. Now, inductive step. Its inductive says assume for any pile that's less than rocks. That's less than n, player 2 is going to win. Now you have to prove it for k plus 1. So you have a pile of k plus 1 rocks, 2 piles of k plus 1 rocks. How can you prove now that this works? Remember, what is your assumption? Any k that's strictly less than n works. Player 2 wins. You just have to prove it for k plus 1. Well, let's say player 1 takes some number I from here. You take the same number of rocks from the second one. What are you left with? Minus I, minus I. The number of rocks left is going to be in this range. Why? Let's say I is 1. Let's say you only took one rock. If you only took one rock, you're left with kk. Yes, with kk, so you're back in this pile. If you only took one rock, then simple induction would be enough. You're trying to prove it for p of k plus 1. You took one rock, you're back to p of k, you're done. But it's not necessary, but they can take any number of rocks. They can either take the whole pile, or half of it, a quarter of it, whatever you want. That's why you need strong induction. It's not enough to go back to p of k. No, any pile that's strictly less than k has to be a given, has to work. Let's say p of k over 2, so on. That way, whatever number of rocks you take from each side, from each pile, like it's gonna bring you back to some given that's true. So when you take some number of rocks from each side, it's like a whole new problem now. But the difference is now your range is within your hypotheses. Okay. This is the sort of problem where you say, hey, where if you try to use simple induction, it's not going to be enough. Because with simple induction, you only know if you have a pile k and a pile k, player 2 will win. Cool. When you try to prove it for k plus 1, if they only take one rock from each side, you were done with the proof. But if they take more and they throw you back to something that you don't have a given for, that's when you're stuck. Like if I here in this scenario, if I take 3 rocks from each, if the players take 3 rocks from each pile, you end up with this scenario, but you only have this as simple induction, and so on. Hope that gave you an idea of strong induction. Other questions? Or questions or problems you want to solve? Anything? So in strong induction, we can put any value less than n because we assumed it is true. But for simple induction, we can only put one value. Sort of, but I just want to emphasize what you mean by one value. So yeah, anything less than n, you're saying the predicate, p of n. You have n minus 1. You have n minus 2. These are all true. Yes, I understand what you're trying to say by value. I'm just trying to tell you what you're saying. You're saying this, like all the predicates are true. This is wrong. For simple, you only have this. You only have this value. So you only have the n pile where player 2 wins. Here, no. If the piles are nn, player 2 wins. If the piles are n minus 1, player 2 wins, and so on. I'm just the wording of, I can see you understand it. It's just the wording of how you say it. You can put any value less than n. Yeah, sure. Like you can use any information, any p of n or any p of k, such that k is less than or equal to n. Like that's the formal way of saying it. Okay, great to hear. I assume there's no more questions. Okay, good. You're welcome. I'll end the meeting. In case you do have any questions, use the forum, even if it's at night or tomorrow morning, and we'll see if we can answer. Good luck in your exam.